Okay. Is it okay like this, or you would prefer a different format in the presentation?
For me, it's okay.
Okay, so
Yeah,
we
it's
can.
yeah, it's there.
Excuse me.
Nothing, man.
Okay, so shall we start? I take this, I guess. Okay, good morning to everyone. On today's presentation, we are at lecture 5, Communication Network Security. And my name is Filippos Pelekoudas, and I'm a researcher in Instituto de Telecomunicações in Aveiro, Portugal. So, to begin with, as Ms. Papaioannou stated in her presentations, we'll explain the teaching methodology, which is based on flipped learning. So we assign students lecture materials to be viewed at home or outside of the classrooms with the help of some handbooks. There are also references in the presentation about which handbooks we take into consideration. And we use a short Q&A test students understanding through a show of hands before starting the session. And also we will use the interactive activities that were referred also on the other sessions. So on today's presentations, we will present secure design principles. Afterwards, we will continue with cryptography used to maintain communication security, and then how to prevent or mitigate network attacks. Most basically, we will talk about DDoS and spoofing. We will start with the design principles. So the design principles that we will refer are 8, which is least privilege, fail-safe defaults, economy of mechanism, complete mediation, open design separation of privilege, least common mechanism, and least astonishment. There are 2 others that you can see in the list. They say the least authority, which is connected to the least privilege principle, and the psychological acceptability, which is connected to the least astonishment. So the principle of least privilege, as the name states, confines how privileges are granted. A subject should be given only the privileges necessary to complete the tasks. So what this means is the administration of a system should give the subjects only the necessary privileges and not more than they need to complete the task. In case privileges is given out of a necessity to complete a sudden task or something that is not predicted, then this privilege has to be taken back after the task is completed. And then we continue with the principle of least authority, which is related to the least privilege, the principle of least privilege, as we said before. Often is considered the same, but we have to make a distinction between what is a permission and what is authority. Permission controls what subject can do to an object directly, what a subject can do to an object directly. However, authority controls what influence a subject has over an object, directly or indirectly. So this is a distinction between the two. We move to the fail-safe defaults. This principle states that unless a subject is given explicit access to an object, it should be denied access to that object. The default action is to grant no access. So again, more or less like the previous, the the privileges and the accesses have to be held at the minimum level. Economy of mechanism. This principle states that security mechanisms should be as simple as possible. When an error occurs, they are easier to understand and to be fixed. The complete mediation principle. The purpose of this principle is to have a complete and ongoing check in every access and privileges is given. The principle of complete mediation requires that all access to objects to be checked to ensure that they are allowed. We can see that there are cases like the Unix systems. If you use Linux, you have noticed that you are asked about a password when you begin an action, sudo, for example, and afterwards you're not asked again about the same password. But there are other cases while the password or the credentials are asked constantly. The principle of the open design states that the security should not be dependent on secrecy of design or implementation. So we don't have to get confused like everything has to be open. But what this principle states is that the designer should not be taking into consideration that by keeping something a secret, it's safe, because secrets of a mechanism usually get away. So we don't have to hold on the perception that the user is ignorant about the design in order to make it safer. Separation of privileges. This principle states that the system should not grant permission based on a single condition. So as many conditions are created, then the safer way the privilege is given. For example, being in the same office with others doesn't mean that we have the same access to a certain folder, which is, for example, a folder that we hold, a SharePoint folder that it's on the office, because some people may be able to read and write, some others may be able to modify others depending on their role. So we don't have to stand only on one duty or on one condition in order to give a privilege and access to files. The privilege of least common mechanism states that this is a restrictive principle. The idea behind is that the mechanisms that are used to reach assets should not be shared, which means that we don't need to use the same mechanisms in every program, in every channel that we use, because through the same mechanisms information can leak, and also if some mechanisms get breached, so we will have the same problem in every other system that uses the same mechanism. Also, a good idea to consider is the isolation through virtual machines and sandboxes, and probably some of you who have experience with testing, you use virtual machines in order not to interact with your system. So you use the virtual machine to create a bubble inside where you can interact with your tests and anything you need without getting in touch with the rest of the system. So something wrong happens, your system remains intact. And finally, the least astonishment. This principle says that security mechanisms should be designed so users understand why the mechanism works the way it does, and the use of the mechanism should be simple. The design must keep a balance between the comfort of the user and the security requirement. And that is because human factors, especially in security, is a big deal. It's critical. And then we will have the psychological acceptability. The security mechanisms should not add difficulty of accessing a resource. So the security mechanism should just act like it doesn't exist. So what the difference between the least astonishment and the psychological acceptability is that the former, this one, it's somehow idealistic, but here we can think that things are not ideal, so we can ask whether the difficulty is unexpected or too much for relevant population of the users. So what should we hold as key points? We underline the security mechanisms, and in order to proceed to a good design and to have a secure system, we have to take into consideration of what is the goal of the mechanisms and what is the design that we need to make, and what suits best. And with careful analysis and design, we will have a good result. Then we will move to more technical part of the presentation, which is the cryptography used to maintain communication security. In this chapter, we will talk about SSL, socket, security socket layer, and TLS, transport layer security, HTTPS, which is common to us because we serve from the internet, SSH, and IP security. So secure sockets layer, it's one of the most wide security services. A general purpose service implemented as a set of protocols that rely on TCP. Provided as part of an underlying protocol suite, so it's not a sole protocol, but rather different ones. So here we can see the protocol stack. SSL is designed to make use of TCP to provide a reliable end-to-end secure service. So you can see here we have the IP level, the TCP, and under. We are mostly in the application layer, if you're familiar with the OSI format. The SSL record protocol provides basic security services to various higher layer protocols. So we can see here the HTTP, the Hypertext Transfer Protocol, which provides the transfer services from web clients to server interaction, and can operate on top of the SSL. And we have three high-layer protocols as part of the SSL: the handshake protocol, the change cipherspec protocol, and the alert protocol. These SSL-specific protocols are used in the management of SSL exchanges. So we will introduce some concepts. There are two: the connection and the session. Connections, if we're talking in OSI terms, is a transport that contributes with the appropriate type of service. Every connection correlates with one session. And sessions, a session is an association between a client and a server. They define security parameters for multiple connections, avoid expensive negotiation. Sessions are created by the handshake protocols, and they define a set of cryptographic security parameters. which can be said among multiple connections. So what SSL connection contains? There are the following: server and client random, a server write max secret, client write max secret, server write key, client write key, initialization vectors, and sequence numbers. These are also parts of a header of a box of data, and each of them are byte sequences that contain the necessary information. I don't know if we want to go more analytical on this. Okay, in case you need, we can move back to explain some particular of these. And the SSL session contains the session identifier, the peer certificate, the compression method, cipher spec, master, secret, and it's resumable, which means it's continuous. That's that's what that aspect. Yes. Okay, so we will continue with the record protocol. The record protocol provides two services: confidentiality and message integrity. Confidentiality handshake protocols define a set key, conventional encryption payloads, while the message integrity, the handshake protocol define a set key for message authentications. Of course, message integrity and confidentiality are two different aspects of security, and they have been explained in previous lectures, I think, by my colleague Maria. And the record protocol provides the header of the SSL stack. So we will continue with the handshake protocol, which is the most complex part of the SSL. Allows server and client to authenticate each other. It negotiates an encryption to send data to the SSL, and consists of series of messages exchanged by client and server. Actually, handshake protocol in the SSL it can be resembled with other handshake protocols that are used in protocol suites like Wi-Fi or other communication protocols. And here we can see, for example, here we can see an example. So the client sends some text, client hello, then the server, in order to establish the first connection, response, and then the necessary byte sequences are sent by the server, and then we have this sequence here, as you can see the picture, in order to finish the protocol. So cryptographic computations, there are two items of interest: the creation of a shared master secret by means of a key exchange, and the generation of cryptographic parameters from a master secret. For this, we use either RSA or Diffie-Hellman or some key public key algorithm. And then we move forward to the transport layer security. It's standardized by the RFC 5246. And it's standardized it's standardized by the IETF to produce an internet standard version of SSL. The key features of this protocol is the version number. It's the same record format as SSL, different only in version values. Message authentication code, which is the same as SSL. Pseudo-random faction, alert codes, and cipher suites. Then we move to a common term, which is the HTTP over SSL, which is the HTTPS. Refers to the combination of HTTP and SSL to implement secure communication between the web browser and the web server. For those who are not familiar with security, there are many extensions in your browser or even in the websites that you can choose to proceed only websites that have HTTPS rather than HTTP, which is supposed to be safer. So it's a combination of HTTP and SSL to implement secure communication, as I said earlier. Can be built into modern web browsers or can be added afterwards. The main difference is you can see in the website when a website has HTTPS instead of HTTP. It is described in the RFC 2818. And when this is used, the following elements of the communications are encrypted: the URL, contents of the document, contents of the browser forms, cookies set from browser to server and from server to browser, and contents of the HTTP header. So when we want a connection initiation in HTTPS, the agent acting as the HTTP client also acts as the TLS client. And there are three levels of awareness. An HTTP client requests connection to an HTTP server by sending connection requests on TCP or TLS SSL. A session is established between a TLS server and a TLS client, and a TLS request to establish a connection begins with the establishment of a TCP connection. So we start on lower levels, and then we end up to the HTTPS, which is on the top of the application layer on an OSI pyramid. And in order to close the connection, the HTTP client sends the message connection :close, and it requires that the TLS close the connection. The transport layer security implementation must initiate an exchange of closure alerts before closing a connection. And unannounced closure could be evidence of some sort of attack. So the HTTPS client should issue some sort of security warning. So the process functions as an extra security indicator. And then we will move to SSH, which is the secure shell. The secure shell is a protocol for secure network communications network communications designed to be relatively simple and inexpensive to implement. SSH client and server application are widely available. And then we have SSH1, the first version, and then the second that fixes the flaws of the first version. And the second, SSH2, is documented as a proposed standard in 90F RFC in the numbers 4250 through 4256. And SSH, also provides client-server capability and can be used for network functions. Here we can see again that is operating on the upper layer of TCP and IP in the protocol stack, and is organized as these protocols on top. So the user authentication protocol, connection protocol, and transport layer protocol. To begin with the transport layer protocol, it provides server authentication, data confidentiality, and data integrity with forward secrecy. For example, if a key is compromised during one session, the knowledge does not affect the security of earlier sessions. So it is based on a server processing public-private key pair, and a server may have multiple keys using multiple different algorithms, thus the feature that we explained earlier about the key being compromised, that doesn't affect other keys. Multiple hosts can share the same host key, and the server host key is used during key exchange to authenticate the identity of the host. Moving forward to the authentication methods, server requires one of the more following authentication methods, which is public key, password, and host-based authentication. The connection protocol runs on top of the SSH transport layer protocol. If we can remember this image here, you will see the SSH connection protocol on the top right, while the transport layer is one layer down. And it's assumed that a secure authentication connection is in use. And then we will talk about port forwarding, which is one of the most useful features in SSH. In essence, actually, port forwarding provides the ability to connect, to convert any insecure TCP connection into secure SSH connection. This is also referred to as SSH tunneling. It is needed to be known what the port is and in which port we want to connect. And as I said, this is a useful security feature. And an application may employ multiple port numbers to use as in the so-called tunnel of port forwarding. So here we can see, for example, on the top of the picture, we see a client application that interacts with a server application through TCP in an unsecured TCP connection, while on bottom we can see that there is the SSH entity that is being added as a security protocol that also can create a secure SSH channel so the client application can interact with the server application. And then we move, I think is the last of this subsection, the IP security. The IP security is on the layer 3 of the OSI pyramid, which is the IP layer. The key points is the capability is a capability that is added on IP version 4 and IP version 6, which are the currently used through the internet IP versions. IPsec has 3 function areas: authentication, confidentiality, and key management. Authentication uses an HMAC message authentication code. Excuse me, I don't recall the HMAC. I think it has a hash-based message authentication cipher or code. Confidentiality provided by encapsulating security payload. And techniques for key management are defined by IKE. IKE is it's a key exchange method, but I cannot recall the initials, excuse me. IPsec provides the capability to secure communications across the LAN network, private and public WAN networks, and the internet. So it can use inside an intranet or the internet or an extranet. Principal features of the IPsec is that they can encrypt or authenticate all traffic at the IP level. We will talk about these two, the encryption and the authentication in the next slides. So we will have some use cases. IPsec grants the means to secure communication across LAN, as we said earlier, and also WAN and the internet. and by creating secure branch office connectivity over the internet, secure remote access over the internet, establishing extranet and intranet connectivity with partners, enhancing electronic commerce security. What are the benefits then of the IP security? The IPsec grants strong security when deployed in a firewall or on a router that can be applied to all traffic crossing the perimeter. IPsec in a firewall is immune to bypass if all traffic from the outside must use IP. The firewall is the only mean of entrance to the organization. So as we can see here, IPsec cannot function only by itself, so a firewall is also a mean of protection on a network. IPsec, as we said, is below transport layer, which is layer 4, the UDP TCP layer. And also it's because of this, because it's under, it is transparent to applications and can be transparent for end user, and it can be provide security for individual users if needed. The routing applications, IPsec can play a major role in the routing architecture for internet working because it ensures router advertisement. It ensures that a router advertisement comes from an authorized router. A router seeking to establish or maintain neighborhood relationship with another router in another domain is an authorized router. A redirect message comes from a router to which the initial IP packet was sent, and the routing update is not forged. The services that are granted by the IPsec allows the system to choose required security protocols, elect the algorithm to use for the services, set up any cryptographic keys required to grant request services. And according to RFC 4301, we have the following services: access control, connectionless integrity, data origin authentication, rejection of replayable packets, and confidentiality. And then we move forward to a more complicated part, which is the transport mode and the tunnel mode. The transport mode provides protection primarily for upper layer protocols. This protection extends to the payload of an IP packet. Examples include the TCP or UDP segment of an ICMP packet, all of which operate directly above the IP. And on the other hand, the tunnel mode provides protection to the entire IP packet. To achieve this, the entire packet adds some security fields, and it is treated as whole payload on the outer IP packet with a new header. So it's like an encapsulation, and because of the encapsulation, the new larger packet, which has, as we said, a payload with the IP header and the security fields, and this packet have a totally different source and destination and cannot be easily recognizable. We will talk about the security association. It's a key concept that appears in both authentication and confidentiality mechanisms for IP. A security association is a one-way logical connection between the sender and the receiver that affords security services to the traffic to be carried. This security association is identified by 3 parameters: the security parameters index (SPI), security protocol identifier, and IP destination address. These are value sequences, except also the IP destination address. These are byte sequences that are referred to as specific security associations. Then we move to the security association database, defines a parameter of associated with each security association, and the parameters that define a security association database are the following: a security parameter index, again a byte sequence that is selected regarding some conditions, a sequence number counter, a sequence counter overflow, anti-replay window, and an AH information, which is the authentication header, an ESP information, which is encapsulation security payloads. Which the first one, the AH, is for authentication, while the ESP information is about encryption. Lifetime of the security association, IPsec protocol mode, and path MTU, which is a path that states how far the transmission can go. And then we move to the security policy database. This is the means by which IP traffic is related to specific security associations. In more complex environment, there are many multiple entries that potentially relate to a single security association or multiple associated with a single SPD entry security policy database. And the following selections determine the SPD entry. So these are the remote IP addresses, the local IP addresses, next layer protocol, which is the IP protocol header, the name of the user identified from the operating system, and the local and remote ports. These are connected with the TCP and UDP port values. So, as we said, we are talking about the encapsulation security payload, which is the cryptographic part rather than the authentication part that we said earlier. Is used to encrypt the payload data, padding pad length and the next header fields of the protocol stack. An optional IVC field is present only if the integrity service is selected as provided by either a separate integrity algorithm or a combined mode algorithm that uses an ICV. Actually, the ICV is not protected by encryption, so it's optional features. We mostly focus on using just the encapsulation security payload. So what do we need to do if some associations use the authentication and others the encapsulation for encryption protocol, but they don't use both? So we have a security association bundle. This refers to a sequence of security associations through which traffic must be processed to provide a desired set of IPsec services. And we are combining these bundles into two ways. The transport adjacency refers to applying more than one security protocol to the same IP packet without invoking tunneling, while the iterated tunneling refers to the application of multiple layers of security protocols effected through an IP tunneling. So, but there is an option that the ESP, the encryption protocol, has an authentication option. So first, users have to apply the encryption to the data, and then use a transport mode or the tunnel mode. So In the transport mode ESP, authentication and encryption apply to the IP payload delivered to the host by the IP header. And in tunnel mode, authentication applies to the entire IP packet delivered to the outer IP destination address. In both cases, authentication applies to the ciphertext. So as we see here, first we use the encryption, then we have the ciphertext, and then we use the authentication. So the plain text is not authenticated rather than the ciphertext. So another way to apply authentication after encryption is to use the two bundle transports, with the inner being the encapsulation security protocol on the security association in the inside, and outside the authentication header security association. Then we move to the key exchange. There are two ways, two types of key management in the IPsec, which is one of them is the manual, where a system administration manually configures each system with its own keys. This actually works better in small environments. And then we will move to the automated, which is an automated system that creates keys on demand for security associations over a system. And then we move to the ISACAMP and Oakley, which are the default automated key management protocols for IPsec. Oakley, which is Oakley Key Determination Protocol, is a key exchange protocol based on Diffie-Hellman algorithm, while the ISACAMP, the Internet Security Association and Key Management Protocol, provides a framework for the Internet key management and provides a specific protocol support for the key exchange. That concludes the section of the security protocols, and we will move to the last section, which is about the security attacks. We will talk about the DOS attack, which is used also mainstreamly. We will talk about the classic DOS attacks, distributed DOS attacks, and DOS prevention and responding. So what exactly is a DOS attack? A DOS attack is defined by the NIST Computer Security Incident as an action that prevents or impairs the authorized use of network system or applications by exhausting resources such as central process units, memory bandwidth, and disk space. So how we can perceive these denial of service in order to understanding more easily? Imagine that I create a program and I want to target one certain resource of a computer or a network. Here, the first example says a central processing unit. So what I do is I create an application that keeps running on the background, that holds the resource of a central processing unit, and this way there is no more space for the CPU to process computer functions that are running at the same time. So we are going up to a point that the computer says I cannot act, so thus the name denial of service, because the computer denies to process its own, the user's own processes. Yeah. And again, but mostly common in the network, we have the bandwidth DOS attack. So again, there are three categories: the network bandwidth, the system resources, and the application resources. I think with the example, we more or less understood what each of them is. So we have the classic DOS attack, the flooding ping command. This is happening in the network level. So if you ever tried from a computer to check the internet, you open the command line and you ping to a certain IP in order to see that your internet is working or to perform some tests. So a floating ping command is a constant pinging of a certain network address. And because so many ping packets are going up to this address, the traffic cannot be handled anymore. So, for example, my computer is constantly sending ping commands to a node here in this institution. Then the router receives, the node receives packets from other nodes, other computers, and these packets cannot be serviced because the node is overwhelmed by my packets. So eventually drops the others and just keep being overflowed by my pings. Then we have the distributed denial of service attacks, and which is actually the same thing as the previous, but it comes from multiple systems. This is the most common of today, the DOS variation. Why? Because one system cannot be intimidated easily by just one computer. So here we can introduce the term zombie. Probably you've heard of it. When, for example, you get an application from the internet running on the background on your computer, which is a malware. What it does, it makes your computer act like a zombie, which means it acts without your own will. So this computer sends requests. For example, there is the zombie application, the software that is installed by not willingly to many computers, and it runs in the background, and all of these zombies computers are now sending pings to a certain address. So here we have the overwhelmed node that drops the packets because it's receiving too many from zombie computers. And other types of DOS attacks are source addressing spoofing, flooding attacks, SYN spoofing, hypertext transfer protocol based attacks, reflection, and DNS amplification attacks. Or they are focused on the same principle of the denial of service attacks. So how can we defend ourselves from the DOS attacks? We have 4 lines of defense: prevention, detection, source traceback and identification, and reaction. So in order to prevent, we can block packet sending from spoofed source addresses if we have figured out which of them are spoofed. Filter can be implemented to ensure that the source address is allocated on the internet service provider. Excuse me. And especially, I guess, SYN spoofing, we can use a modified TCP connection handling code. We can also block IP-directed broadcasts. For example, we know that a certain computer is a zombie, so we can block it. Block suspicious services, and CAPTCHA, which is quite annoying, but kind of useful in these cases, because the websites, for example, that you usually see CAPTCHA when you try to open a new account on a website. And imagine that if a zombie computer is constantly overwhelms the website on the web service by opening new accounts, we have problems of denial of service because of terms of memory of the web service database and the terms of how much traffic the website can handle. So CAPTCHA is a kind of simple and easy way to define that the computer is actually, that there is a real human behind the computer or not. So to respond to these attacks, we must have details on how to contact the technical personnel of ISP, traffic filtering upstream, details on how to respond to the attack. We have to have implemented anti-spoofing, directed broadcast and rate-limited filters. And ideally, we can have network monitors, monitoring services and software, not the screens. IDS, which is intrusion detection systems, that we will talk in later lectures, to detect abnormal traffic. Also, to identify the type of attack, we need to capture and analyze the packets. There are softwares like this for this purpose. ISP trace packet flow to the source, contingency plan, update the incident response plan. After a certain attack, we have to re-update our incident response plan. And this is where we come to the end of the presentation. To summarize, we talked in the first section about the principles of secure design. If you remember, it's the least privilege, fail-safe defaults, economy of mechanism, complete mediation, open design, separation of privilege, least common mechanism, and least astonishment. Each one of them that states a different purpose in order to decide and design a good security implementation. Then we talked about the SSL TLS protocol, the HTTPS on the application layer, the SSH, the secure socket, the IPsec, and finally we ended up with the DOS, denial of service attacks. We described the attacks. We asked how the basic mentality is behind the denial of service attacks, and we said some things about the defense against the DOS attacks. That was all from me. Thank you for your attention. If there are any questions, please.
It seems that I don't have questions.
I don't know how to consider this, but thank you.
If there are no questions, we can close this session and see you this afternoon for the session number 6 with Fabrizio.
Okay, thank you very much.
Thank you very much, Filippos.